Should I start? Okay. All right, well, why don't we get started? Hopefully everyone can hear me. I'm Chris Wysopal. I'm the CTO and co-founder of Veracode. I've been doing application security now for probably 12, 13 years, I think. And Veracode has been around for about 7 years. And for the last 5 years, we've been collecting a lot of data from all the application security testing we're doing. So my talk today, we see the future and it's not pretty, is using that data and trying to use it to be predictive. So we call it the State of Software Security Report. We've come out with 5 volumes over roughly 6 years now. And there's a lot of reports that have been out there for longer. Reports from Verizon, Data Breach Incident Report, and TrustWave has their, I think they call it their Global Security Report. And they report about incidents. So it's like, this is how the guys got in, right? So it can help you learn about maybe you have that same problem and the same tactics are going to be used on you. So these are very valuable reports, and a lot of security programs are built, and a lot of things like the top 20 critical security controls from SANS, things like that, are built based on seeing what went wrong after the breach happened. Well, the State of Software Security Report is actually not looking at incidents, it's looking at the vulnerabilities we're detecting in the applications. So we look at this as more predictive than the incident reports, because these vulnerabilities are going to be there for years, right? If they made it into the software, they're going to be there for years. And it's a good way to see what the long-term trends are going to be around application security. So the data set we have is about 22,000 applications over an 18-month period. And you probably can't see some of these numbers up there. But these different parts of the pie chart are, green's financial services at 27%, 9% is orange, software industry, 6% technology industry, 6% telecom, 4% government, 3% business services. So you can see it's a pretty diverse set of, it's not just financial services, it's really kind of mapping to the software that enterprises use to run their businesses. And on the right here, you can see the distribution of web apps in blue versus non-web apps that are not mobile in green, and mobile apps in orange. So you can see our customers are mostly concerned, or our customers mostly have web applications that they want tested. So that is the majority of our data set. But since we have so many applications, 22,000, even at 3%, we're still talking about hundreds and hundreds of samples that the data is made up of. This is the overall distribution of the different languages. I'm going to talk a lot about slicing this data by language, because I think it's pretty interesting to see the differences by language. And as we went from volume 3 of our report to volume 4 to volume 5, we've seen Java in the green here shrink a little bit from 52 to 50. .NET is staying about the same. We're seeing C and C++ actually go down from 12% to 9% over 3 years. And we're starting to see Cold Fusion stayed about the same at 2%, but we're starting to see mobile apps take up more of the slice of the pie, going from 6% to 8%. So we're sort of seeing the mirror of what application development is at enterprises with our data set. And so this is the data we have. We have our customers send us their executables, their binaries, and we have them fill out this metadata. We know what industry vertical they are. We can look that up by the customer, but they tell us who supplied the application. Did I download open source? Did I buy it from a vendor? Did I have it outsourced, or did I build it myself? That's what we consider the supplier. So we can slice the data by who supplied the application, start to see is open source better than vendor code or vice versa. We know what the application type is. We know basically rough categories of what it does. Is it a security app? Is it an operations app? Is it a customer support app? Is it a marketing app? We can start to see our different apps written using different levels of security rigor. We have them give us an assurance level, so we know how critical this is to their business. Is this, financial transactions, in the millions, operating, facing the internet, a highly critical application, or perhaps what just happened to American Airlines today, their global flight reservation system went down, kind of a critical app. Now they have 800 planes grounded. To apps that they care a little bit about. Maybe it's a marketing app. They care about their brand. So we can see if people are using different practices or holding their vendors accountable to different practices based on the type of app. So we have some interesting data in the language and the platform we know. And then what we do is we take that application and we scan it with static or dynamic analysis. And we're able to determine, we look for different sets of vulnerabilities or security defects, if you will, in the application. And for each one of those, we know what line of code it was on, we know when the scan was performed, and we know what type of defect it is. So this is what we generate. We generate the scan data. And then using that, we can come up with some metrics. We can calculate some values, such as how many flaws does this application have? What percentage of flaws in our total data set is a particular vulnerability category? So we calculate these things to try to figure out what's going on in the world of application security. Are people creating more or less SQL injections today rather than tomorrow? So one of the things in this volume we dove down deep in is slicing it by language type or platform type. Because you might have Android is a different platform for a Java application versus a Java web application. So slice it by platform type and language. And the other thing we looked at was what did people remediate? How quickly did they remediate things, and what did they choose to remediate? So that's a lot of what I'm gonna talk about today. So I'm mostly going to talk about the latent vulnerabilities, what's sitting there in these applications that we've discovered. And of course, a lot of vulnerabilities will never be exploited, right? The app is reachable by attacker. The attacker doesn't care about that application. Maybe that kind of vulnerability is really hard to exploit. So those factors certainly go into this. So when you're talking about latent vulnerabilities, you have to really kind of talk about the attacks to some degree to try to understand what the weight is. Unfortunately, we don't have a lot of attack data that goes all the way down to vulnerability type. You see it a lot with Sql Injection. Sql Injection attacks are pretty easy to know. You see a database dump, and those are kind of easy to figure out. But a lot of these other vulnerability types, when was the last time you heard like an app that was breached in the news was breached because of cross-site scripting? I'm sure a lot do. A lot of our customers care about cross-site scripting and they fix them, so there must be some reason for it. But it's more rare. So if you look at this chart here, I've compared the percent of web applications affected in the orange, which is the Veracode data. So those are the latent vulnerabilities we're finding on average, how many applications are affected by a class of vulnerability. And then in the sort of the bluish green there is percentage of hacks that we know were due to this attacking this vulnerability class. And we get that from the Web Hacking Incident Database, which is the best place we found for this data. I think is Andrew Hay in the room here? He was saying in the last presentation by Patrick Florian, we don't have a lot of data in application security, and that's the thing we constantly struggle with. Like, we have really accurate data of latent vulnerabilities, but I need other data to make sense of that, right? I need the base rate to some degree, and so this is the best I could find. But I think it stacks up to show you relatively comparing latent vulnerabilities with SQL injection at 32% and 22% of the attacks of web applications using SQL injection. That kind of makes sense to me, right? It's pretty prevalent, it's easy to find, it's easy to exploit. We're seeing it's being used 20% of the time. That makes sense. Now, cross-site scripting, we find 68% of applications have cross-site scripting. So if you're an attacker and you can come up with techniques for using cross-site scripting to compromise an app, you'd probably do better than you would with SQL injection. But we only find 10% of the hacks are actually due or have been detected and reported as due to cross-site scripting. So we're getting a big discrepancy there, and we try to explain it. Maybe it's this cross-site scripting is harder to exploit to the means, to the ends that the attacker wants. Information leakage we see is affecting 6% of apps, but it's only mentioned in 3% of the reports of a breach. So it's probably used a lot, but we only know about it happening pretty rarely. Cryptographic issues really stands out as something that doesn't make sense to me. We're seeing it in 53% of the apps that we test, yet it's only reported as being used 2% of the time. To me, that just seems like a complete reporting error. I think if an app has crypto issues, it's probably being attacked more than 2% of the time. And then finally, command injection, we're finding it's in 9% of applications. Command injection is pretty easy to exploit, right? You just kind of inject the command you want to execute, or you figure out the way it's being parsed, and you encode it the right way. Yeah, we only see 1% of the time. So I think this slide, more than anything, shows that we need better attack data so that we can understand which latent defects we should be prioritizing to fix. From this, really the only thing I can say is if you have SQL injection, you probably should fix it. These other ones, it's a little harder to understand how to prioritize. Good question? Right, it's a specialized skill set. Right. Right. No, that's a possibility. Even things like weak random number generation, which we find all the time, sometimes it's difficult to exploit that because you have to come up with a prediction. Right. Maybe that's the 2%. That's the 2%, right? Yep.
Well, cryptography is a very broad category.
Yep.
So maybe inherently in terms of attack complexity, let alone the skills that might be related. But presumably that includes corporate cryptography like storage of data.
Right.
Attackers on
Sure.
and then if there's weak cryptography
Right. Like a man-in-the-middle attack. Right. Right. Yeah. Right. So, this slide sort of is my call for better reporting of what are the root causes of breaches. Because without that, then I don't know how to weight some of these different issues as far as what are you going to fix first. So a lot of people will weight things based on, what's the criticality, what's the impact if that vulnerability is exploited, but it doesn't take into account what's the chances it's going to be exploited. And this is trying to get at what are the chances it's going to be exploited. From here we can say, yeah, it looks like a lot of those SQL injection vulnerabilities are going to end up being exploited. I mean, this is only the top 4 categories. After this, it was under 1%. And we know there's more than 5 defect categories that matter. So if in your organizations, if you can push to have things more detailed reported, that would be good for the community as a whole. So our big overall number we find is that 70% of the applications that our customers had us test failed to meet the test criteria that they specified, or the enterprise security policy is another way of putting it. And so that's generally bad. And this is apps that are being tested before they get put into production, or they might be apps that they're purchasing, or they're having an outsourcer, build for them. So the majority of applications aren't meeting the policies that are put out there. And this is sort of the detail of three different kinds of policies that our customers use. Some hold all their web-facing web apps to, say, the OWASP top 10. That PCI compliance uses it, so they say, hey, that's what I want in my organization. That doesn't really work with non-web apps, so people use the CWE SANS top 25 a lot of times for that. And then people come up with custom enterprise policies. They just say, I just don't want any SQL injection and cross-site scripting. That could be a custom policy. Or they could say, I don't want anything that has a high criticality impact, and I want to eradicate those. So those would be custom policies. So we basically looked at all the apps that we tested, and we basically took the set of vulnerabilities we found, and we held it against OWASP top 10. So if it had one defect in the OWASP top 10, it failed. It was in this 87%. We held it against, if it was a non-web app, we held it against the SANS CWE top 25. And if it was an enterprise app, and they had an enterprise policy, we held it up against that. So I think the one thing that, I can take, besides saying that the majority of apps out there are secure, is enterprises are more lenient than the OWASP top with their policies. The OWASP top 10 is being more strict number because the majority of the apps we're looking at are web applications, and they're falling into they would fall into the OWASP top 10 bucket that we selected. This is another overall set of all the applications we looked at. This is the build over build improvement that we saw. So we have a lot of customers who just test once, and they say, hey, thanks for telling me about my vulnerabilities, and they go away. But we also have customers that say, hey, I'm going to build this into my development lifecycle, and I'm going to test every build that I'm building. And so this is the progression. What we come up with something we call a security quality score, which is weighted based on the number and severity of the different vulnerabilities we find. And this is how they improve over time. You can see these whisker charts as one standard deviation, and the line in the middle is the median. And the width, I guess, is the number of samples. So you can see that we have less customers that have done 9 builds with us than 1. Right? I guess it looks like it's a little like. Right, probably not. Probably not. So I'm not sure how that's calculated, but that's basically it's the sample size. And so you can see that in general, it slowly increases over time, build over build. And it's kind of interesting when you get to build 9, it kind of dips down a little bit. And we sliced this on an earlier data set with just 5, and it kind of dipped down after the 5th one. And so, what would make it go down, which would probably be there's a lot of new functionality there. So there's a lot of new security defects that were created, say on average between build and build 8 in our customer set data set. That's where it seems like a lot of new vulnerabilities came about. So what I would think is over time, this would kind of oscillate around some sort of a steady state or average out. So one of the big findings we found from looking at all our data was SQL injection has plateaued at 30%. 32% of all web apps are affected by SQL injection. And when we did our earlier reports, we found that there was a slight trending down. We saw our first couple reports, it went from 36% to 34% to 32%. But our last 3 reports, going back to beginning of 2011, it's staying remarkably constant. Over tens of thousands of web applications, we're seeing this constant of 32% of SQL injection. So the set of apps is changing, right? We're not testing the same apps over and over again. That wouldn't make sense because, if we've told someone about a vulnerability and they fixed it, it wouldn't make sense to bring this in. So this is only the first time we're looking at an application. So this is a constantly changing set of applications. So what this tells me is for every app that's getting fixed, there's a new app that's being written that has a vulnerability in it. So we're sort of seeing this sort of constant of, if you look at the whole set of web applications on the internet, of course some are brand new, some are old, some have been secured over a long period of time, but this is constant. So if you're an attacker, you're always going to be able to find sort of 1 out of 3 applications that you bang on hard enough, you'll find a SQL injection vulnerability. So I find this is pretty interesting, because this means that there has to be some major change to the way we're building applications, the languages we're using, the techniques we're using, maybe there's regulation, maybe there's liability. Something has to disrupt this ecosystem of software development, or we're just sort of stuck with this 32% number. Forever. So we'll have to see how this changes. And then, so this is overall, over the last 3 volumes of our report, over 3 years, how different vulnerability categories have changed in the percentage of web apps that are affected. So you can see cross-site scripting has sort of gone from number 2 to number 1, but it's hovering around the same number. Information leakage has gone down. Carriage return line feed injection has actually gone up. Cryptographic issues has gone down a little bit over the last 3 years. Directory traversal is staying pretty steady. This is another pretty common one, right? Like, that's pretty easy to exploit. Many people saying, hey, I've exploited a directory traversal issue. Well, we're finding it's in 49% of the applications out there. So if you get good at finding those and good at exploiting those, you can have a field day. Here at Sql Injection, you can see that 3 years ago it's at 38%. We've seen 2 years ago and today it's staying pretty steady at 32%. This insufficient input validation kind of crept up, and this is kind of a bias of our testing. We added a lot of new tests in the last 18 months to look for specifically insufficient input validation. So whenever we see a change, a sharp change up or down, we always go to look at to see if we have testing bias. So we've investigated all those other changes and found that we didn't make any significant changes, but we did with the insufficient input validation. So now I want to dive in and slice the data by programming language. This is something that I presented, in volume 4 before, and we never looked at the data this way, and people said, I really want to understand, does the selection of programming language make a big difference to the number of vulnerabilities in the app? So, this is to some degree, grounding this in reality with these are the programming languages that people are using. So this is called the TIOBE index, and this organization uses, it's sort of like the Billboard 100 for computer programming languages. They use numbers of engineers programming the language, number of courses being taught, third-party vendors using it to figure out what's sort of the popularity of these different languages, because you can't get an absolute count. You have to use a proxy. And so this is the popularity of languages from number 1 to number 10. It's interesting, C and C++, they break out separately, where we lump them in together because the same compiler can compile C and C++ code and output it. So we lump them together. But if you lump them together, C and C++ would be the highest category, 26% of apps being written in it. And then we get Java being really number 2. And then, interestingly enough, Objective-C is number 3. And Objective-C was nowhere on this chart 5 years ago. Does anyone know why Objective-C is number 3 now? iOS, right? So because a major platform standardized on this, it grew to prominence. And then we have C#, which is actually the only one that's really trending down. So this probably isn't good for Microsoft and .NET. That's going down. PHP staying about the same, Visual Basic the same, and we see Python and Ruby on the rise. So we actually cover all of these except for Python and Perl at Veracode, but our Visual Basic and Ruby support is so new, it's only about a year old, that we don't have a good data set yet. So we don't we don't use those. So this is what we see. So that's the global sort of index. What we see is for the web apps, we see 56% are Java, 28% .NET, 10% PHP, 4% Cold Fusion, 2% C and C++. I don't know who's writing web apps in that, but I guess some people are. Bad idea. Probably a bad idea to write anything in it. And then non-web apps, Java is still number 1, followed by .NET, but then we see C and C++ tick up here to 29%. So I think if we had an ISV-only data set, C and C++ would be by far the biggest, but since our customers we have ISV customers, but we have more enterprise customers, enterprise developers typically use Java and .NET. And then on the mobile platforms, they break down 56% iOS, 34% Android, and 10% A2ME. So people are actually still writing apps for BlackBerry. Yep. Yep. Yes. Yep. Right. So we audit mostly enterprise applications for large enterprises. There's a whole bunch of C and C++ development that's happening that we don't get to look at, like embedded systems. There's a huge amount of C and C++ there. ISVs do a lot of development in that, and probably our ISV data set is probably around 20% of our data. So I think the fact that we don't look at embedded systems and ISV is a smaller part is what's driving that. So here's the vulnerability prevalence if we just slice all the apps we looked at with Java. And so this is the percentage of apps that are affected by a particular vulnerability. So code quality is things that can cause business logic problems, typically using the wrong operator in a comparison. People like to compare strings to objects, things like that, which is not the right thing to do in Java. That can end up with code quality issues. So it's not surprising that we find that in 82% of applications. But then some of these other categories we're finding really endemic. Character return line feed injection, cross-site scripting, cryptographic issues. These are some of the things that we find in a lot of Java applications. You can see Sql injection here is 31%, so it's a little bit below the average by language. So Java might probably in the range of error. But if we're finding 32% total and Java is the biggest slice, that makes sense. So that's percentage of applications affected. Then I have data showing, this is probably hard to read, this is the share of total vulnerabilities found, how that's trended over 3 years. So we're seeing cross-site scripting stay pretty much the same, character return line feed injection stay the same, information leakage stay the same, we're seeing encapsulation stay the same. We're actually seeing directory traversal go down slightly, and cryptographic issues went down slightly over the 3-year period from 5 to 2. And so I look at that and say, well, why are those trends happening? I think a lot of those could be education of the development community. They could be educated on, you need to do crypto better. I think a lot of it, though, is frameworks that people use. So if a new framework comes out that becomes popular that does crypto really well, or protects people from doing crypto wrong, that's going to drive down the crypto error rates. And another analysis I want to do is slice one language by frameworks and seeing if frameworks can help. Here on this chart, which you probably can't read very well, is the percent improvement from build 1 to build 2. So what this is telling us is what defects are development teams determining are the most important defects for them to fix that they're getting on first. What are the highest in their priority list? And the ones in blue are the categories that have the highest vulnerability distribution, and the ones in orange are the ones that aren't high. And you can see that the prevalence of it and the distribution of it doesn't seem to come into factor, because we have high prevalence things being fixed and we have high prevalence things not being fixed. So the things that are not being fixed
OS command injection at 8%. So we told them about a whole bunch of OS command injection issues. They only fixed 8% of them between build 1 and build 2. Cross-site scripting, they only fixed 14%. That was the second worst. Time and state errors, they only fixed 15%. Insufficient input validation, 15%. Sql injection, they only fixed 16% of the Sql injection issues. So we told them a whole set of them. On average, they fixed 16% between build 1 and build 2. So I don't have a good explanation for this, only to say like there might be no rhyme or reason on how developers prioritize what to fix, at least in general for Java applications. You'll see for some languages it starts to make sense. Any question? This is, I believe this is all Java applications. So the whole set. So I have the same data for .NET. I don't want to go through every one of these because you'll be bored to death, but we can post the slides out there. Lisa say, things like Sql injection, like here in the middle, 30%, about the same, maybe a little bit than in Java. So it's interesting to compare the top vulnerabilities across language, which I'll get to. Again, code quality is number one. One of the interesting things, though, here is cryptographic issues is higher with .NET at 62% versus 55% for Java. So that's a significant difference, 62 versus 55. So there must be some reason. The documentation's not as good. Maybe .NET developers get better training in crypto. But that seems like a significant enough difference to have there must be some reason in the development environment why that's happening. Now, if we look at the things that .NET developers fixed first, is interesting. The number one thing they fixed first are buffer overflows. They actually fixed 59% of the buffer overflows that we told them about. And if I go back and tell you how many apps are affected by buffer overflows, only 1%. So because .NET, you have to really use the unsafe code pragma and write native code to get a buffer overflow. It's fairly rare. So it's a fairly rare problem, but it's interesting to see that developers took it really seriously. It was rare, but they fixed 60% of them, or 59% the first time, which makes sense to me. .NET developers also fixed 25% of the Sql injection vulnerabilities that we told them about between build 1 and build 2, versus Java developers only fixed 16%. And these are sets of thousands of applications, so this must be telling us something about the way Java developers think about fixing Sql injection versus .NET. And I don't have a good explanation, but it can't be random. So let's go on to PHP. So PHP, the top issues, cross-site scripting, directory traversal, information leakage. It actually does a little bit better on Sql injection than the other languages, which actually kind of surprised me. We hear about PHP applications being so buggy, and the developers are not, most experienced developers. But for things like Sql injection, it actually did pretty well. See, it's fast, secure, and bug-free PHP. So if we look at Sql injection, it's fallen down here, but it's staying constant at 6%, 7%, 7%. It's just some of these other categories went up, so it made it fall down. But if we look at what they fixed between first time and second time we looked at the code, the PHP developers were all about fixing Sql injection. They fixed 54% of the Sql injection. So they did better than the .NET guys or the Java guys by far. So there's something about PHP apps. Maybe there's more PHP apps running internet facing, or maybe the PHP developers got the memo, but they are taking Sql injection seriously, much more so than the Java and .NET. And maybe it's because more PHP apps are internet facing. I'm not sure, but they're doing the best job of fixing the most critical and prevalent vulnerabilities, which I found was pretty interesting. Yep. Perhaps. I mean, the ease of fixing is definitely a factor. If something is easier to fix, it'll be more likely fixed between that first iteration and then the second time. So maybe the .NET and Java apps in general are just more complex, and it's hard to fix the issues. Yeah. Sure. So that would require 2 extra pieces of data, which I'd love to have, but they're really difficult. One is I need to know what developer wrote the defect, which is it's not that easy to do. You can do it with new code if you're in the check build system, but most apps have a lot of legacy code in them, and so that's going to pollute that. And then you'd have to know what the developer's training or awareness was. So that would be good in predicting whether training and awareness actually helps or not. I'm not sure we have good data to tell whether training developers actually makes more secure applications. It makes sense, but I haven't seen any data that shows that. Yep. Sure. So I kind of did that. So I kind of did that. I'm not comparing any of these languages to C and C++. I'm keeping that separate because their class of vulnerabilities are completely different. So, right. So maybe you're introducing the next slide. Well, we have to do Cold Fusion first, and then I'll get to something. So Cold Fusion is interesting because it seems like it's really, really bad around three different issues. And they just happen to be cross-site scripting, Sql injection, and information leakage. So it's just interesting that, you know, if you look at if you pick the random Cold Fusion app, which are easy to find on the net because they have that nice CF extension, you know, you have a 95% likelihood of finding an app that has cross-site scripting, 72% likelihood that it has Sql injection, and you're going to get all kinds of help attacking it because there's 62% chance that it has information leakage. So, you know, I can understand why we hear a lot of Cold Fusion apps being compromised, and it's probably because of the prevalence of those issues. Unfortunately, I didn't have the build-to-build improvements with Cold Fusion. I had to replace it with this Cold Fusion developer icon. But you can see it's holding steady with cross-site scripting and SQL injection. Information leakage seems to be going up. I'm not quite sure why that's happening. But most of the other categories are staying the same. So here's where I combined them together. And I took the top 5, you know, I just eyeballed it. I don't think there's any science, but the things that were showing up the most in at least a few of them to show how Cold Fusion, PHP, .NET, and Java compare to each other on these 5 categories. And it's really interesting. The PHP, the .NET, and the Java are almost exactly the same when you look across SQL injection and cross-site scripting. They're very similar, and Cold Fusion is kind of sticking out like a sore index finger here, I guess. But it's radically different, which just shows, you know, the way that these apps are constructed, the way that they're developed is radically different than the way people build .NET, Java, and PHP apps. On the other hand, when you look at crypto issues, Java and .NET are pretty high, and PHP and Cold Fusion are low. But I think that's just because those apps don't have a lot of crypto, right? They're not bothering with crypto. They're not sort of enterprise class sensitive information type apps. So if you don't have the functionality, you can't have the vulnerability. So that's kind of how I explain that. Directory traversal, you know, Cold Fusion seems to be different. So the way that, you know, people are dealing with files must be very different in Cold Fusion, and it makes it harder for developers to screw up. But command injection for PHP and Cold Fusion was a little bit higher, which shows me that the way you execute commands on PHP and Cold Fusion is probably riskier. So looking at it this way, I think it's really easy to look at a programming language and say these are the things I'm trading off and that I need to worry about. Typically, you don't get to pick your programming language based on the vulnerability prevalence of that. There's other business factors that are more important, like can I hire developers that write that? Do I have a legacy code base that I'm going to leverage to do that? But once you've made that selection, you can look at data like this and you can say, hey, I'm building a Cold Fusion app. I better really be careful about cross-site scripting and Sql injection. I got to test that early. I got to educate my developers. And so you can use it that way to say sort of what am I inheriting from the platform and how do I need to compensate for that. And then I thought this one was really interesting. So this is the first to second test improvement by language. And unfortunately, I didn't have the data on the Cold Fusion for this one. But you can see that Sql injection, PHP developers taking it seriously, .NET a little bit, Java developers not so much, cross-site scripting, PHP taking it more seriously too. Crypto issues, there were really no crypto issues in PHP that were fixed. There was a very low percentage that were found and none were fixed, so that's 0. But we can see Java developers are caring about crypto maybe a little bit more. In command injection is interesting that PHP and .NET, they're caring about it equally, but Java far less. So maybe it goes to what Steve was saying, it's the complexity of the developer understanding how command injection could work in these huge enterprise Java apps that they don't really think it's a risk. So then I did C++, and C++ are very different languages, very different from the other languages because it's not type safe. And the error handling is sort of ad hoc, right? People can do exception handling, but a lot of it is ad hoc. So error handling is really bad in C++, which can lead to a lot of code paths that are unexpected, can lead to a lot of vulnerabilities. But then we have buffer management errors, buffer overflows being really high. Those don't exist in the other platforms. Then we have our friend cryptographic errors still existing again. But then we have numeric errors. So there's a whole bunch of categories here in C++ that you have to worry about if you've selected this as your language you've inherited it. But there's some good news. We've actually seen buffer overflow steadily make progress. It was 27% of the defects we found, went to 20%, and now 16 over a 3-year period. So people have really got the memo about buffer overflows, that these are bad, they're going to get exploited. And this is, if Sql injection is staying the same and we've come to complacency dealing with this sort of risk that's just out there on the internet, that is not true for buffer overflows. That is going to be on its way to extinction over time. Unfortunately, buffer management errors, which another heap corruption type issue, we saw an uptick between volume 3 and volume 4, but then we've seen it remain about steady, went from 18 to 16. Numeric errors we've seen not going away, stayed at 14%. We saw crypto issues pop up in the latest report. This potential backdoor kind of I think is a selection bias. I think we've gotten more accurate. We've got a lot of feedback from customers about, we don't want to see these. They're not really potential backdoors, even though we think they're potential backdoors. So we've kind of tuned that one down. They're like, we don't want to hear about backdoors because we don't know what to do with it. The problem with potential backdoors, you have to do a lot of investigation. We're reporting things like, there's like this huge mass of obscured data in your application. You might want to check that out. And they're like, don't tell us about it. Now here on the percent improvement, it's interesting. The number one category is API abuse. So that's a lot of times in C, there's like a set of APIs. You have to call one, then the other. The classic one is after you call chroot, you got to call chadir. But there are other APIs that you have to call in sequence, and if you get one of them wrong, we flag it. They're actually fixing that 89% of the time. So this is, maybe Steve's right, this is something developers can understand. They're like, oh, I forgot to call that, so I'll fix it. Maybe that's an understanding issue. This is really heartening. They're fixing 74% of the buffer management issues we flagged, so they're taking that very seriously. Buffer overflows is only at 34%, so sometimes I think those might be harder to fix. Buffer management errors are things like, I calculated the size wrong, or my loop, constraint was wrong. Buffer overflows are typically things like stir copy and mem copy. And they're taking a lot of these things pretty seriously. Numeric errors, untrusted search path, directory traversal. So I think in general, I should have done something about the count of issues fixed, not just the category, so I could compare C and C++ with Java.NET. But just by looking at the width of these bars compared to some of the other ones, like here was we have hardly any that are over 25% improvement. And here we have all of these categories. So we're finding more defects, but they're also taking them seriously and fixing them with C and C++. Yep. Right. So I should explain this. So this is only first time we looked at an app. This is the first build we've looked at. This is build 1 to build 2 improvement. So I have a little bit of data here, how I'm doing on time, on iOS and Android. And so we did the same thing for iOS and Android, and running late on time here, so I'll just speed through it. But number 1 is code quality. Number 2 is cryptographic issues. 64% of the Android applications out there have cryptographic issues. So they're embedding keys, they're embedding passwords, they're not implementing SSL correctly, they're not doing proper error handling, they're not doing certificate validation checks, they're not using the proper encryption algorithms. And so this is clearly an education problem. These people have been told you gotta use crypto in that Android app or that iOS app, but the developers really don't know what they're doing. Same thing with Objective-C. We see Objective-C really just in these 3 big buckets up there: error handling, cryptographic issues, and information leakage. We're seeing Objective-C apps. And then here's some comparison even with BlackBerry application, so you can see the overall vulnerability distribution. You can see in iOS we actually get buffer management errors because Objective-C is a non-type safe language. So here's my summary slide, and this is where I get to make my predictions. So with 70% of applications overall failing, our prediction is this is going to make the lives of CISOs more miserable over the next couple of years. They have a lot of security debt that they've inherited. The average tenure of a CISO is about 2 years. So they've inherited a lot of application development that is just churning out really bad applications that's going to cause their organizations to get breached. And the fact that 70% are failing, whether they're buying or building those applications, means that they are going to be a constant pain point for that CISO. The other one, where it's the Sql Injection plateauing at 32%, we see that as the rise of the everyday hacker. We used to call them script kiddies back when I first got into this, right? I used to run the script, which just ran the little tool to exploit a known vulnerability, right? Well, I think that exploiting Sql Injection is a little step above the script kiddie because it's not completely turnkey. You have to know something, but you don't have to know a lot, right? You put a single quote in the field, you see if you get an error message, then you go to a Sql Injection cookbook and you start going through and trying these different things out. So it's a little more difficult than script kiddie, so this is why we call it the everyday hacker. But I just told you that the last 2 or 3 years of development is shipping 32% SQL injection vulnerability. So that means that there's a lot of low-hanging fruit out there for people who are willing to pick up some skills. So eradicating SQL injection has turned out to be a pretty thorny problem. So something that easily exploitable, we know how to fix it really well, and this just shows that the security people aren't getting through to the development people. And this is where I get to mention Gene Kim and get a free beer later tonight. But Gene said in his talk that, this is where the security guy is banging his head up against the wall because he's not able to affect any change. He's not able to affect any change in the processes about how the applications are built. And so the fact that we can eradicate this means more pain and job dissatisfaction for the application security people who, when there's a breach of a web app, they're like, hey, weren't you supposed to find this when you did your manual pen test? And they say, I can't find all the SQL injections in my manual pen test. We need to fix it in dev. And they say, no, we're not going to fix it in dev. So that's where that frustration occurs. Question or comment? I haven't looked at it, but I should. I'll definitely take a look at that. Okay, and then finally, we think that this is not going to be able to stand, that 64% of Android apps have crypto issues and 58% of iOS issues, and we think that that's going to change over time. So I think the way that that's going to have to change is the platforms are going to have to make it so that by default, you're encrypting your data transmissions, or by default, you're encrypting when you're storing data, and sort of flip it around. So the developer really has to do a lot of work to do it wrong. So that's a prediction that we're banking on the platform providers to listen to us to do that. But I think unless they do that, we're not gonna see improvements there, and it's going to be easy to do crypto attacks on mobile apps. So that was all I had for slides. If there's any final questions. Yeah. John, are you a CISO or are you an application security practitioner? I know you've been in the latter. So yeah, our jobs suck, right? Everyone's frustrated that, we know how to fix these things, but the business doesn't really put in the energy or the time